Hi everyone, my name is Yue Zhang from Central South University. I'm very glad to be here to introduce our recent work. Our paper is named Toward Efficient Image Denoising, a lightweight network with retracting supervision-driven knowledge distillation. As we all know, image denoising is a fundamental but critical task. With assistance of deep neural networks, considerable success in image denoising has been observed in the past few years. Previous works mainly focus on improving denoising performance via establishing complex modules or depending networks delicately, which may execute efficiently on powerful GPUs. However, it's discouraging or even impossible to enable these models to run efficiently on platforms with limited computational resource, such as surveillance cameras or smartphones. As a result, it's necessary and urgent to decrease the model size and maximize the performance of small models as much as possible. So, how to solve such a problem? First, we need a lightweight model, but this will lead to performance degradation. At this time, knowledge distillation is required to improve the model performance. Knowledge distillation accomplishes the model compression and computational cost reduction through the teaching paradigm between high-performance teacher networks, usually with massive computational costs, and lightweight student networks. However, these distillation methods are specifically designed for high-level tasks, and they bring no performance gains when applied to image denoising. Therefore, in this work, we first design a lightweight image denoising network (LUNet) for RGB image denoising by carefully considering the challenging trade-off between denoising performance and efficiency. Secondly, we further propose a novel and flexible distillation algorithm with retracting supervision to improve LUNet. Extensive experiments on multiple synthetic and real-world datasets demonstrate the effectiveness of our distillation algorithm for the single image denoising task. Especially benefiting from the retracting supervision, our proposed distillation framework allows for arbitrary high-performance teacher networks. In particular, by incorporating both the knowledge of the teacher and ground truth in retracting supervision, our RSKD algorithm is more flexible and no longer requires a similar structure for teacher and student networks. When the LUNet combines with RSKD, it would achieve effective and efficient image denoising. Since a lightweight model is still absent for RGB image denoising, we present a lightweight U-shaped network, LUNet. It will also serve as a baseline model for the subsequent distillation algorithm. The left figure shows the overall architecture of LUNet and the structure of key building blocks. LUNet is based on unit architecture with a depth of 4 and depth-wise separable convolutions. Specifically, LUNet has an encoder-decoder structure, where the input image is a noisy image and the output image is a clean image. LUNet has 4 encoding stages and corresponding decoding stages. Given an input noisy image I, the network first applies a 3×3 convolutional layer with step size 1 to project the input image to the feature space. Then, the subsequent encoders encode the projected features. In the later step of each encoding stage, the downsample block subsamples the feature maps to reduce the memory consumption. After decoding, we obtain a feature map of the same size as the input map. Finally, the feature map is projected into the pixel space using a 3×3 convolutional kernel layer with step size 1 and output by adding the input noisy image. Especially, as shown in the right table, LUnit obtains the comparable denoising performance to origin unit by using less than 14 times Gmax and less than 10 times parameters. The naive distillation algorithm usually takes the L1 loss for the teaching process. X is the corrupted image with noise, and Y is the ground truth. Here, Y hat is the output of student, Y bar is the result of teacher. Subsequently, we find that since the naive distillation algorithm assumes that the restored image by the teacher network are completely trustworthy, they discard random lies in the real distillation process, including distillation failure. In other words, naive knowledge distillation suffers from a degraded problem. It ignores teachers' imperfection. As shown in the figure, the pipeline of our proposed retracting supervision-driven knowledge distillation (RSKD) framework. We introduce retracting supervision to help the student network learn efficiently and use MAR-led as a teacher. Especially, we propose a data-adaptive sigma to acquire randomness. We introduce an auxiliary network branch attached to the student network to learn the variance. This would allow the student network to capture the distribution completely. We use L1 loss to enable the auxiliary network to capture the data-adaptive variance, where sigma is the output of the auxiliary network, where alpha is a hyperparameter to balance different aspects of loss. As a result, the multivariate Gaussian distribution composed by the output of the teacher network and the data-dependent variance terms forms the new retracting supervision. During training, RSKD distills the student network via retracting supervision with the assistance of an auxiliary network. After training, we only need to keep the origin student network LUnit for testing. Therefore, we do not introduce additional computation in the student network. We report the quantitative results on both synthetic and real-world datasets. The real-world denoising performance on SIDD present in Table 1. We also compare the computational complexity of the latest methods, including the model parameters as well as the practical running time. FAN is chosen as the efficient baseline model. It is worth noting that our LUnit has a higher performance, nearly 2 dB. Our LUnit effectively weighs computational cost and performance. In comparison with the origin unit, LUnit has comparable performance with less computation. As shown in Table 2, our RSKD algorithm an average gain of 0.85 dB to LUnit for synthetic experiments on Gaussian noise. This further demonstrates the superior performance of our method for simple noise. Qualitative result on SIDD. We show the visual comparisons in figure. Compared with the result of FAN, LUnit can produce favorable recovery results. Moreover, our distillation algorithm makes the origin LUnit more effective in recovering texture information without color distortion. We present the Ablation Studies to analyze the contribution of each component of our model. The evaluations are performed on the SIDD datasets. As shown in Table 3, compared to the naive KD supervision, our retracting supervision drive KD design can provide effective enhancement to the baseline. We explore the importance of the information in the retracting supervision. As shown in Table 4, we choose the necessity of the existence of the auxiliary network. We further explore the different choices of the variance item. We generate them in two ways. As shown in Table 5, It has better performance on PSNR. We suppose that this approach enables the student network to identify the shortcomings of the teacher network and thereby learn the teacher network thoroughly. Besides, both of them has higher SSIM than that of the origin unit. This may mean that our approach can effectively leverage the knowledge of the teacher network to enhance the performance of the student network. We explore the contribution of different teacher networks in the proposed distillation framework, as shown in Table 6. Our distillation algorithm has no restrictions on the teacher network, offering considerable flexibility. In summary, we make contributions for efficient image denoising from two aspects: efficient network structure and destination algorithm respectively. We first design a lightweight U-shaped network, LUNet, which has lower computation cost and fewer parameters than the origin unit. Then, we propose a novel destination algorithm to improve the performance of LUNet. Finally, supported by the RSKD algorithm, LUNet accomplishes efficient image denoising. We expect that our work will encourage further research on the knowledge distillation algorithm for other low-level vision tasks. That's all. Thank you for your listening.